Well, here in 4.5, what we're basically doing is taking the concepts that we've been doing here in Chapter 4 of the maximizing and minimizing that we get from derivatives and critical points, and we're incorporating them into word problems. So you know how it's like when we first form an equation and we take the derivative of it, which finds our rate of change, then by setting the derivative equal to 0, we can find the maximum rate of change, or we can find minimum rates of change. And in word problems, what this is going to refer to is things like maximum cost, or minimum area, or minimum cost, maximum profit. We do a lot of those in the business world. If you want to find what's going to give us the maximum dimensions, things like that. And it's all built on this whole concept of your derivative. Okay? And in the word problems, we call these optimization problems. Optimize, get your optimal maximum, your optimal minimum value. Okay? And just typical, like we talked about, your goal is to get an equation. That's the hard part, just form your equation. And then from there, you're just going to take your derivatives, test some critical points, and then go from there. So let's take these ideas and let's do example 1, which is number 4 in the book. And if we look at this problem in depth, what it's saying is that basically you have a rectangle, and with that rectangle, your base is just sitting here on the bottom of the x-axis, so it's just touching that. Now the upper vertices is touching a parabola, and this parabola specifically is y equals 12 minus x squared. So if I was going to kind of, not that we need it, but I know that y-intercept up there is 12. Okay. Now the question asks us, what is the largest area that this rectangle can be, and what are dimensions? So what we want to know is what kind of rectangle can I fit in here, so that way it's going to give us the most area possible and still fit within this parabola. So it's like I drew one here in blue, but I mean technically, couldn't I have another rectangle that maybe did this? And then the question is, would that rectangle actually have larger area than the other one would? Okay, so that's what the goal is, what we're trying to find. And I'm just going to focus on this blue one for just 1 second. We're going to go from there. So let's go back to this blue one. All right, let's talk about this. In general, we need to form our equation, because remember that's the hard part, is just getting an equation. Well, it says since we're maximizing area, I'm going to try to build an area equation, where area in general is just length times width. Okay, well, let's look at this rectangle right here. What would be the length? It's like, what is the length of this base? And what would be the width, or what would be this height? Well, if I start here at the origin, and I go this direction, I know that has a length of x. If I start there and I go back, that's also x. What about the height, though? Well, the height, since it goes from basically a y value of 0 up here, what is that y value up there? Well, you can think of this as like a coordinate. That has gone x over to the right. Well, to get up, since it's sitting here on the parabola, every y value on that parabola has a value of 12 minus x squared. So it says y has to be 12 minus x squared. Okay, so that's really, really going to help, because the length of the whole base of that is 2x, and the width, which is the height, is 12 minus x squared. And there is our area equation. Okay? And honestly, you could not have done that unless the vertices, it's very important that it said the vertices of that rectangle were on that parabola. Okay. All right, now from there, now that we have our equation, we want to go about the whole optimization process. We want to find the whole maximum value. So that's built on the derivative. Okay. Well, actually, real quick, before we even do the derivative, let's go back and finish out the equation to where it'll be easier to take it. So the area is going to be 24x minus 2x cubed. Okay, now that'll be a lot easier, so we don't have to use the product rule, right? So the derivative of the area, the rate of change of the area with respect to that part of that length, is going to be 24 minus 6x squared. Okay, so that represents all rates of change, but we want to find specifically the maximum or minimum rate of change. So we're going to set it equal to 0. And solving this out, so 6x squared is equal to 24, or x squared is equal to 4. Doing a plus or minus here, we get an x value of either plus or minus 2. Well, you know, the whole goal is to finding the dimensions of a rectangle, and obviously the dimensions of a rectangle can have an x value of negative 2, so we're really just going to focus on an x value of positive 2. Okay, well, to test whether that one was a true max or min, remember we're going to put this on a sign chart and we're going to test it with our derivative, so against a prime. Okay. And number to the right of 2, we can say maybe 3. And we're going to plug it right here in our derivative. So 24 minus 6 times 9. Well, 9 squared is 3 squared is 9. 9 times 6 and 24 minus that, it is definitely going negative. If we test a number to the left of 2, let's say 0, that's pretty simple. So 24 minus 0 is positive. So what we've just found is to the left of 2, our slope is positive, which means we're increasing. To the right of 2, our slope is negative, so it's decreasing. So if we're going from up to down, that means we definitely had to have a max sitting right there at 2. Okay, so now to fully come back and answer the questions, because the question says, what is the largest area? So the area is going to be the whole length. So it's 2 times the x value, and then times the height, which is 12 minus 2 squared. So 4 times 12 minus 4, which is 8. So the area is equal to 32 square units. Since it didn't really give us dimensions, we're just going to do square units. And then specifically, if it asked us for the dimensions, you could say it's basically the base is 2 of x's, so it's 4 by, and then the height was 12 minus 2 squared, which was 8 units. Okay, so that would be the answer to example number 1 or number 4 in the book. So let's try this again, looking at example 2, which is number 8. Example 8 says that we have a pea patch, a rectangular pea patch, and it has an area of 216 meters squared. And what we have done here is we have divided into 2 equal parts. So here's my overall pea patch area. Here's a divider coming down the middle, dividing into 2 parts. So I don't know, we can say that this length over here is x, and then all across this way, we can call that y. So everything that direction and everything that direction, we'll just say. Okay? And what we need to do, the whole goal, is to find the dimensions that's going to require the smallest total length of fence, and then how much fence is actually going to be needed. So it's almost like we're looking for the smallest, we're looking for a minimum value this time. Alright, well, they didn't really help us out here in the sense of we have 2 variables, we have x and y. And anytime we have 2 variables, you basically need 2 equations. You need however many variables is how many equations you need in order to solve it. So if we had 3 variables, like an x, y, z, we would need 3 equations. Since we have an x and a y, we really don't know anything about each other than the fact of we can maybe take some of this information and build equations. So I know that area is equal to length times width, so we can say in this case x times y, right? And then I know the area is 216. Okay, so that I know. But I still have x and y in that equation. So let's see if we can get another one. Well, this whole concept of what we're trying to do is find the perimeter. So let's see if we can get an equation for perimeter. Okay, and perimeter? Well, perimeter is everywhere we're going to put that fence. So we're going to put the fence here on the left. We're going to put it down that middle, so that's also x. We're going to put it on the right. That's x. So we've got a total of 3 x's. We're going to put it along the top, and we're also going to put that fence down along the bottom. So we have a total of 2y. All right. Well, going back to our basic days of algebra, we know that any time that you have 2 equations you need to solve for them, you can either use a substitution method, an elimination method, or you can use matrices. Okay. I'm just going to do a substitution because that's really simple here. Let's come over here to this area 1. Let's solve it for one of the variables. I don't know, let's say y. Okay. So we know that y is equal to 216 over x. Okay, just, solving it out. And now what I'm going to do is take this y and replace it right up in there. So perimeter is now 3x plus 2 times y, which is 216 over x. Or we can say perimeter is 3x plus 432. And I'm going to write that as x to the negative 1 because I'm about to take a derivative and I want to be able to see that exponent. Okay, so here's one of our main equations right here. And we're going to focus on the perimeter because, again, it's asking us how much dimensions does it need to be in order to find the smallest total length. So we want to find a minimum value for the perimeter. All right, Alright, so let's come up here. We write this equation. So I know perimeter is 3x plus 432x to the negative 1. And let's take the derivative of it so we can start finding this minimum value. So it'll be 3 minus 432x to the negative 2. Or we can look at it as maybe 3 minus the 432 over x squared. Okay? And like before, now the next step, in order to find the max or the min value, we need to find the critical points. So set this equal to 0. Okay, so we basically have 432 over x squared is equal to 3. Or if we take the reciprocal of both sides, we can say x squared over 432 is equal to 1/3. So multiplying this out, times 432 just to clear some fractions. There we go. We get x squared. Well, 432 divided by 3 is 144, or x is equal to 12. Again, we're going to ignore the negative part since we're talking about the length or this whole side of a pea patch, and we obviously can't have negative. Alright, so if I test, come back up into our derivative for perimeter, and if I test 12, let's go to a number to the right. Okay, remember we're going to test right in there. A number to the right, let's say 15. Okay, well 3 minus 432 divided by 15 squared. Well, 15 squared is 225. So 3 minus 432 divided by, try to type this in our calculator real quick, 225, you basically get 1.08, so it's definitely positive. Okay. Let's test a number to the left of 0. I don't know, 0 is always, or left of 12. Always 0 seems to be fun, but look at that. If I go back in here to my derivative and I test 0, what's going to happen to that denominator right there? Well, you can't divide by 0, can we? So what it's showing is that is actually one of those asymptotes where it can't be 0, so we can't test 0. Let's test maybe 1 instead. Well, 3 minus 432 over 1 squared is 3 minus 432, which is definitely negative. So this is telling me that my slope is negative, which means my graph is going down. This is telling me my slope is positive, so my graph is increasing. So if I go from down to up, I've definitely come across a minimum value at 12. Alright, so let's wrap this up and answer the questions that they want us to find. The dimensions for this pea patch. Okay, well, x, which was 12, and then y, technically, so it's going to be 12 by, how do I get y? Well, you can do one of two things. I would probably go to your area equation. So, area is x times y, so 216 is equal to 12y, and if you divide by 12, you get y to be just 18. So the dimensions are 12 by 18 meters. And then the perimeter then, so all this fencing that's going to go around all this perimeter, so go back to your perimeter equation where it's 3 times x and 2 times y. So it's going to be 3 times 12 plus 2 times 18. So the overall perimeter should give us a total of 72 meters. Alright, so there's the overall perimeter, there's the overall dimensions, and we have just finished this problem. So on to the next one.